So today we'll see discuss about ODEs. Okay, what are ODEs? Ordinary differential equations. Fine. Ordinary differential equations. Now, before beginning for the ordinary differential equations, okay. Okay, before beginning ordinary differential equations, okay, we will see a bit generalization. Okay, what is the generalization of it? So, differential equations, you have differential equation, and any differential equations can be divided into two types. Okay, it can be divided into two types. One is ODEs, okay, which has a independent variable, single independent variable, okay, and then there are PDEs, okay, which has more than one independent variable. Okay, so you understood. So differential equations can be classified into two types. One is ODE, which has a single independent variable, and another is PDE, which is referred to as partial differential equations, and they have more than one independent variable. And this is the reason why, while discussing about optimization, we did gradients. We are doing like regression cost function or loss function was a function of weights W0 and W1. And what we were doing? We were doing dou E by dou W0 equal to 0 and dou E by dou W1 equal to 0. Okay. So like that, we were minimizing that, and that's where partial derivative starts to come. Okay. So there were two independent variables, W0 and W1. Okay, and our job was to find which W0 and W1 to take so that you have the least error or the least cost function or the loss function, right? Okay. So this class will focus on ODE, and the next subsequent classes will deal with PD. Okay. So what is ODE? ODE is nothing but we'll go to ODEs. We'll write a nth order ODE first. Just a general version. Okay, general version. You can write that nth order ODE in terms of, say, it is a function. It is a some function phi, okay, which has x, okay, which has the dependent variable y, independent variable x, okay, and then all the possible derivatives, dy by dx, then d2y by dx2, then so on, maybe dny by dxn, okay, equal to 0, right? So this is the nth order ODE for you, okay? So what is the, so y is a function of x, so therefore x here is the independent variable, and as per our definition we have a single independent variable, and here there is only a single independent variable. Y is a function of x, so therefore y is dependent on x, therefore y is known as a dependent variable. Okay, and therefore we are considering the derivative of y dependent variable with respect to the independent variable x, and we are considering further higher derivatives of that. Okay, fine. This is the general version of nth order ODE. Okay. So yes. So solutions of ODE, like we will take one example question. Take for example this equation that ODE, simple ODE, dy by dx is just equal to 0.2 xy. So it is telling us that there is a single independent variable x, and y is changing with respect to x as dy by dx, and that is equal to 0.2 xy. Okay. So now my question is, can you find what is our job here? Our job is to find what is the function y. What is the function y, right? What is y of x? So can you tell me what is y of x? You don't need any numerical method here because it's a very simple ODE. What to do? It's a separable ODE. Okay, what to do here? Can anyone tell how to solve it? you do dy by y equal to 0.2x dx, isn't it? And then try to integrate them. Okay, then what you will get? The left hand side will give you ln y. Okay, and then 0.2 is constant coming outside, and integral x dx, that you know it will be x square by 2, and then some integration constant c. Okay, so therefore you have ln y equal to 0.1 x square plus c, and that I can write y as e to the power 0.1 x square, then some new c. New c, maybe we can say d, another constant. Okay, e to the power c. Okay, e to the power c we can say d. Okay, so this is your equation. Okay, this is the constant. This is the constant we are looking for. Okay. So this is the constant you are looking for, right? Okay. Now, a very important question I would like to ask everyone, okay, is what are the solutions for this? You have the solution y equal to e to the power 0.1 x square plus d. So now, for d equal to 1, you have the solution 0.1 x square plus 1. For d equal to 20, you have y equal to e to the power 0.1 x square plus 20. For d equal to 20.1, you have y equal to e to the power 0.1 x square plus 20.1. And you can take infinitely many choices of d, and that will give you infinitely many such y solutions, and all of those are different, right? So what does that mean? That your solution is not unique. You got it? That's the plan. Okay, this is how you should think. Okay, you should not just see and apply your thoughts. You should think why it is unique, why it is not unique. Okay. Okay. Now, so the solutions are not unique. When it will be unique? When it will be unique? So I am telling that if you put d equal to 5, then the solution is y equal to e to the power 0.1 x square plus 5. And this is unique solution, right? This is a unique solution, right? Because if you plot y versus x, then it will be just like a exponential equation, isn't it? It will be just like an exponential equation, right? And it's a single function, right? So why, how can we fix a d equal to 5? What does it mean? Note that when you put y of x equal to e to the power 0.1 x square plus d. Okay, how can we find d? At x equal to 0, y of 0 equal to e to the power 0.0 plus d. Okay, so y of 0 minus 1 equal to d. So d depends on the initial condition. So if you fix your initial condition, you are fixing d, and that is giving you a unique solution. You got the idea? Got the idea, no? So that means d depends on the initial condition. The initial condition. Why we are telling initial condition? Because it is the value of y at x equal to 0, the starting point. Okay, d depends on that. And if we fix y0, the initial condition IC, then we are fixing d. Then we are fixing d value. And if we are fixing d value, we are getting a unique solution. We are getting a unique solution. Is that clear? So if you fix your initial condition, you are getting a unique solution. If you don't fix your initial condition, you are not getting a unique solution. So such kind of problems are known as initial value problems. Such kind of problems, okay. So such kind of problems where we fix the initial conditions, that is y of 0 equal to some c, okay, are referred to as initial value problems. Okay, are referred to as initial value problems. So therefore, most of the time, you will not see someone asking you, you recollect your bachelor's degree or your class 12th exams, okay, always dy by dx equal to 0.1 x square will be given, and then something else will also be given, that given that the initial point y of 0 is 5. Okay, then this will give a unique solution. Okay, good. So now you know that how differential equations we can handle, and how it can give you unique solution, and when it can give you infinitely many solutions. Now you know. Okay, good. So let us start with our initial value problem. Okay, so we'll start with initial value problem, also known as IVP. Okay, also known as IVP. Okay. So we will take the question here. Suppose we have the ODE. Suppose we have the ODE given by, okay, suppose we have the ODE given by dy by dx equal to f of x comma y of x. Okay, and with the initial condition, okay, with initial condition, what is the initial condition? Y at x equal to some x naught is equal to y naught. This is the initial condition. So what will happen? What we know, what is guaranteed to us? What is guaranteed to us? What is guaranteed to us? The guarantee we have is it will have a unique solution. Because initial condition is chosen. Since initial condition is already fixed, it will have a unique solution. That's what we learned in our previous slide. So it is guaranteed that, so we know that y will have a y. So this ODE 1 has a unique solution, isn't it? We know that already, right? Why we have a unique solution? Yeah, initial condition is already given to you. Got the idea? Okay. So now, okay. How can we solve this? So always what happens is, always you always cannot solve ODE. Okay. I mean, always you will not have a simple ODE like this. Okay. Always you will not have a simple ODE like this, which you can do the integration and solve it like this. Okay. I mean, get the solution like this. Always it is not the case. For example, I will tell you dy by dx equal to some sin x, okay, whole square, cos x whole square, okay, plus, can you give me some complications? X cube y square e to the power x. Okay, can you solve this ODE? I don't think it has a closed form solution. I mean, I don't think if you can write y equal to something, something. Very difficult, very difficult. Okay, so there, hmm? Right. Okay, so she will give us the solution after it is done. Okay, okay, good. So, yeah, it might be solvable. Okay, but it will be extremely difficult. Okay, so I suggest, so everyone has an assignment. Try to solve this. Okay, using your methods, what you have known so far. Okay, okay. So therefore, usually you cannot solve so easily these things. Therefore, what happened is we can devise numerical methods for that. Okay, I mean, we can develop, we cannot get a closed form solution like y equal to something we can write, but we can generate the data and the data will be the solutions. Okay, we got the idea. Instead of telling that y looks like this, what we will tell is we will generate the data set. That is, at x equal to this, we have this y value. At x equal to this, we have this y value, this y value. At different points, we will tell that this is the data set. Okay. We will generate the data set using numerical methods. That is the objective. So we will learn two different methods today. How we can solve the ODE, initial value problem. Okay. We will do several examples and you can appreciate that also. Okay. So the two methods are Euler method and RK4, Runge Kutta fourth order method. Those two are very nice methods. Okay. And Runge Kutta method is very accurate method as compared to the Euler method also. But Euler method, we should know that there is a method like this, how we can generate the solution. Okay. But RK4 is the suitable choice every time. We will see why that is the case. Okay. Fine. Now, suppose you have this. I hope that in your scientific computing course, did you learn about finite difference? Hmm? To do what? What you can do now? Huh? What you can do? Forward difference. Huh? So what is forward difference? Tell me. So you can write dy by dx as yi plus 1 minus yi divided by xi plus 1 minus xi. Right. And xi plus 1 minus xi is nothing but a constant, that is step size. It is with your control. It is the step size you have. Okay. So this is nothing but then yi plus 1 minus yi divided by h. Right. You understood? Hmm? So now, can we replace that? So we have dy by dx equal to f of x comma yx, right? So can we substitute this equation here? So we have now yi plus 1 minus yi divided by h, plus there is some error term, that is order of h. If you truncate it, we are truncating it, right? We are truncating it. So we will have an error term. That doesn't matter, but there will be some error in your code. Okay. In your data, there will be some error. So that is order of h error. Okay. Actually, it is big. Order of h is big. Okay. So that is equal to f of xi comma yi. Isn't it? Do you agree? Yes. So what can we do next? We can write yi plus 1 because that's the value at the next iteration. What is yi plus 1? It is the value at xi plus 1. Do you agree? Yi is the value at xi. So yi plus 1 is the value at xi plus 1. So our job is to find yi plus 1. In terms of yi, we want to find the future value in terms of the past. So therefore yi plus 1 can we write in terms of yi plus 1? So yi plus 1 is equal to yi plus h times f of xi yi, and there will be some order of h error term. Isn't it? Do you agree? Do you agree? Is it correct? Is it correct? How many of you think it is correct? How many of you think it is correct? How many of you think it is correct? Only one I am seeing. How many of you think it is correct? How many of you think it is incorrect? Incorrect. How many of you think? Incorrect. Huh? Uh-huh. Order is an order. It doesn't matter whether it is positive or negative. Order is an order. We are just looking into the magnitude of it. Which one? Full. Okay, I will repeat again. Okay. So we have the differential equation dy by dx equal to f of x comma yx. Did you understand that? Right? What we do if we cannot solve a closed form solution, therefore we are looking for a numerical method to solve it. So for a numerical method, we will discretize our domain. Okay, we will not consider it as a continuous domain, rather discretize it. Therefore, the independent variable which you are looking now from x0 till some point x, okay, we are dividing into equispaced points. Okay, those equispaced points are x1, then this is x2, then this is x3, x4, like that. And x1 minus x0 is same as x2 minus x1, is same as x3 minus x2, and that is referred to as a step h. So you start from y equal to x0, that is y0, because it is initial condition. Then your job is to find what is y at x1. Okay, what is y at x1? But you know x1 is equal to x0 plus h. Okay, at equidistant, you are finding the next value, next value, next value. Okay, so therefore, what we did to understand more clearly, we discretized dy by dx using forward finite difference method. That is dy by dx, we wrote it. This is not correct also, not to say equal to, but rather an approximation. Okay, because this is an approximation. And then we are saying it is equal to yi plus 1 minus yi, the forward. Forward means we will take the future value. Yi plus 1 minus yi divided by xi plus 1 minus xi. Right? Xi plus 1 minus xi is always fixed because we have equidistant step size. So that is h. But what we don't know is yi plus 1 minus yi. Right? So, but dy by dx, you already know that dy by dx equal to f of x comma yx. Can we replace this equation here? So yi plus 1 minus yi divided by h plus order of h. This order of h comes from the finite difference method, is equal to f of xi comma yi. Our job is to find the y value at the futuristic value, that is point, that is yi plus 1. Our job to find yi. No, yi is in the past. That is already we can get. If you want to find y1, it will depend on y0. Y0 is already given to you. Y0 is given to you here, right? So you can find y1 based on y0. After y1 is found, you can find y2 based on y1. After y2 is found, you can find y3 in terms of y2. That's what is going on in neural networks. That's what is going on in deep learning. The futuristic value depends on the past. So this is incorrect. Rather, you will have yi plus 1 minus yi plus order of h square is equal to h into f of xi yi. Therefore, our job is to find yi plus 1. So you will get yi plus h f of xi comma yi, and then order of h square will be there. Okay. So we are evaluating. Okay, we are evaluating yi plus 1 at xi plus 1 using the past values, of y, that is yi, and x, that is xi. Okay, so therefore it is a forward method. Forward difference we have applied, so it's a forward method. We are evaluating yi plus 1 in terms of yi and the value of the function at the past, that is xi yi. Mind you, this method is of order h square. Okay, I mean the error of this, you will not get accurate result, but the error will be order of h square. Okay, so therefore, fine. So this is an explicit scheme. In technical jargon, you can call it an explicit scheme because everything on the right hand side is known. All RHS is known. Otherwise, it would be called as an implicit scheme. Okay. Can you check that all RHS are known to you? You know YA, you know H, you know F at XAYA, right? So therefore, everything you know, and you are evaluating YA plus 1. Okay. Good. So this method which you just saw, okay, I will write it here again, but without the order term. So we will do yi plus 1 equal to yi plus h times f of xi yi for the difference for the ODE, for the IVP, actually initial value problem, dy by dx equal to f of x comma y of x, okay, given that y at x naught is equal to y naught. And this method is known as the Euler method. Euler method. Okay, this is known as the Euler method. Okay. Good. So we will see that. We'll do some examples in this case so that you will know better what is happening. Okay. Okay. I'll write the question here. Okay. So use Euler method. Use Euler method to solve numerically the initial value problem. So you can only use Euler method in initial value problem. In any other case, Euler method is not applicable. Okay. So use Euler method to solve numerically the initial value problem. Du by dt is equal to minus 2t u square, where initial condition is u at t equal to 0 is equal to 1. Okay, this is the initial condition. You can take h is equal to 0.2. Okay. So compute. So what you will do? So you know u at t equal to 0 equal to 1. What is your Runge-Kutta method? So you know du by dt equal to minus 2t u square, right? And that is equal to f of u comma t, isn't it? So what is the Runge-Kutta method? Runge Kutta method is ui plus 1 is equal to ui plus the step size, that is h, times the f of ui ti, isn't it? So what you can write here, ui plus 1 is equal to ui plus h. What is f of ui ti? Minus 2 ti ui square, right? So h already told it is given that you take 0.2. Okay. So u1 is equal to u naught plus h minus 2 t naught u naught square. Okay. So what is u naught? Can you tell me? From here you know u naught equal to 1 at t naught equal to 0. So u naught equal to 1, h is 0.2 minus 2 into t naught is 0, u naught square is 1 square. So u1 is 1. Okay, is it okay? Similarly, can you compute what is u1 actually? u1 is equal to u at u at t equals to t1. Okay, what is t1? t1 equal to t naught plus h. t1 equal to t naught plus h. What is t naught? 0. h equal to 0.2. So u at t equal to 0.2. Okay. So t1, u1 is nothing but, so you understood, right? So u1 is nothing but u at 0.2. Understood, no? Got the idea. So what is u1 we got? 1. Can you find u2, u3, u4, so on? And tell me. And tell me. Yes, start doing. Okay. So similarly, what is u2 you are getting? u2 is nothing but u at 0.4. That is equal to 0.92. u3, that is u at 0.6 is equal to 785. Okay. I think 7845. u4, u at 0.8, 0.50706. Is it correct? Okay. This is, I think, u5. u4 is u at 0.8 equal to 0.63. Sorry. Right? Fine. u1, that is uc, oh, u1 already got. Okay. Now, okay, fine, good. You have done a good job. Okay. Now, check this, that can we solve this ODE? What is given? See the board. Okay. du by dt equal to minus 2t u square, right? With given that u of 0 equal to 1, isn't it? Is it given in your question? U of 0 equal to 1? Or I am wrong? U of 0 equal to 1? Okay. And this is correct? Du by dt equal to minus 2t u square? Correct. Correct. Check your notebooks. So how can we solve it? Du by 2u square equal to du by u square equal to minus 2 dt t dt, right? We can take integration on both sides. So this one is nothing but u to the power minus 2 du. That is nothing but u to the power minus 2 plus 1 divided by minus 2 plus 1 is equal to minus 2 outside t square by 2. Then there is a constant c of integration. Agree? So yes, u to the power minus 1 divided by minus 1 is equal to minus t square plus c. Okay. So u to the minus 1 is equal to t square plus some constant d because minus c. Okay. Or if we can put it minus c, no issue. Okay. Good. So what it means? U equal to 1 by t square minus c. Fine. Okay. So u of t is this. Now tell me that u of t you got is analytically 1 by t square minus c, and given that u of 0 equal to 1, given that u of 0 equal to 1, so u of 0 equal to 1 by 0 square minus c equal to 1, already given to you. So you will get c equal to minus 1. Agree. So therefore what is the full solution? Therefore u of t is now equal to 1 by t square plus 1, if it follows that IBP, right? Now u at 0.2 is equal to 1 by 0.2 whole square plus 1. This is equal to 1 by 0.04 plus 1, 1 divided by 1.04. This will come around 0.96, I think, right? You can do your calculator check. Okay, 0.96. Okay, what you were getting? You were getting 1. Okay, anyway, u at 0.4, can we compute? 1 by 0.4 whole square plus 1. This is equal to 1 by 1.16. Can you tell me the value 1 divided by 1.16? 0.862. U at 0.6. 1 by 1.36. How much? 0.75. 735. U at 0.8. 1.64. U at 1 equal to 1 by 1 plus 1. 0.5. Okay. These are exact solution. Do you understand? These are exact solution. Because we used integration method and we solved it, these are actually exact solution you are getting. These are actually the exact solution. Can you compare with your numerical solution what you got? Can you compare? You were getting, I will tell you, okay, you got u1 equal to 1. Whereas here you are getting it 0.96. You see the discrepancy. What is the error? 0.04 is the error. Understood? Now u2, let us see. u2 you got 0.92. Here u2 you are getting 0.862. So you see the error is 0.06. The error increased. The error increased. First step the error was 0.04. Next step the error is 0.06. I guarantee that the error further step will increase even more. What is u3? 0.78. Right? So what is it correct? Then u 0.6 is again 0.73. Okay. Then see u5. Okay. Then see u4, 0.63. Okay. And you are getting 0.609. And u5, which is u1, 0.5096, you are getting 0.57. Sorry, 0.5. Okay. Understood? So there are some discrepancy, but it is approximating somewhat. This is Euler method. What I suggest is your assignment, next class assignment is H we take very big actually. H is taken as 0.2, which is very big actually. So take H equal to 0.01. Okay. Then it will be very lot of steps actually. 100 steps it will be. To reach to 1, that will take 100 steps. So you have to do 100 calculations. Maybe. Okay. Find your job is take h equal to 0.01 and find u 0.2. Okay, 0.2. U at 0.1 and u at 0.2. Okay, find that and submit. Okay, good. Okay, so everyone understood Euler method? Everyone understood Euler method? So this is one question we practiced. Okay, we can practice similar several other questions. But I think like now you already understood how this Euler method works. Okay. So Euler method is actually very much dependent on the step size h. So therefore you have to take the step size very low to make it more accurate. Okay. You can use a for loop that we will see Python implementation also in today's class. So now let's move to the next method. Okay. That is known as the Runge-Kutta method. Okay. And we will see the Python implementation of both the things. We will also see what kind of different packages are there in Python for your ODEs. Okay. So how many of you already have gone through Runge-Kutta method before? Runge-Kutta method in bachelor's maybe? No? No one. Okay. Runge-Kutta. Fourth, we'll not see any other method. We'll directly go to the best method available. Runge-Kutta fourth order method. Okay. Same issue. Same issue. Okay. We will tell you. So I suggest this is a very good book. Okay, it is available in library also, I think. Lot of copies. I suggest get that. You can do a lot of problems also as practice. Lot of problems are there. Okay. So a book which looks like yellowish and all, you can get. Okay. So good. So our job is to solve ODE, that is du by dt equal to f of some t comma u, and given an initial value u at t naught equal to say eta naught. Okay, this is our initial value problem. This is the initial value problem we have. It is a constant. Just for notation I'm writing. Or you want to write something else? What you want to write? U of t naught equal to u naught. Simple. Simple. U of t naught equal to u naught. Simple. Okay. Good. So this is the initial value problem we are studying. Okay. Then Runge-Kutta method tells you what is the Runge-Kutta method? What is Euler method? Ui plus 1. The future value depends on the past. Forward. So here also similar thing will happen. Here the future value will depend on the past. But the method is very highly untrivial. Highly untrivial. If you want a derivation of this, you can let me know. I can cover it in another class. Okay. But here I am directly telling you the method. And we will do a problem based on it. You need to have a workout on this problem. Okay. I'm not telling you how this method is coming. If you want me to tell how this method will come, we can do in a separate class, derivation. Okay. So now Runge-Kutta method tells that you can obtain a numerical solution to this initial value problem as follows. Similar to Euler method, what is Euler method tells? Ui plus 1 is equal to something which depends on ui. Isn't it? Same as Euler method, ui plus 1 should depend something on ui. So same thing in this Runge-Kutta method. Ui plus 1 is equal to ui plus hold yourself. Okay, because what else is coming is a bit complicated. Okay. So, but it has meaning. It has meaning to it. 1 by 6 K1 plus 2 K2 plus 2 K3 plus K4. Okay. Where K1, K2, K3, K4, I will define each of them now. Okay. You understood? This is the method. Okay. Where K1, I will write it. Where K1 is equal to H, the step size, times F, okay, in F at Ti Ui. K2 equal to H times, H means H into multiplied. The function value at Ti plus H by 2, comma Ui plus K1 by 2. Okay, did you understand? K2 depends on value of K1. K2 depends on the value at K1. So if you are finding K2 first, you are making a mistake. You have to first find K1, then find K2 because K2 depends on K1. You will also see that K3 will depend on K2. K4 will depend on K3. Okay. K3 equal to same thing, H times F at Ti plus H by 2, comma Ui plus K2 by 2. Okay. And K4 is equal to H times F at Ti plus H, comma Ui plus K3. Okay. This is a highly accurate method. This is a highly accurate method. Okay. So we will solve a problem so that you can understand this. Okay. Shall we solve the problem? We will solve the same problem I have given you for Euler. And at the next step, after solving Runge-Kutta method, we will compare the exact solution. We'll make a table. We will make a table of exact solution, Euler solution, Runge-Kutta solution, to make you aware that which method is the best method. Okay, we'll do that. Okay, so you understood. So maybe let me make you a bit more understanding possible. Okay, so Runge-Kutta fourth order method. Okay, fine. So Runge-Kutta fourth order method. Okay. So what it tells us that if you have this ODE, okay, du by dt equal to f of t comma u, okay, and initial value problem is being given to you as u naught is u t equal to t naught is equal to u naught, okay, then I am telling you that Runge-Kutta method tells you the following, that is ui plus 1 is depending on the past ui plus there is something nice here. Can you tell me what is nice here? The nicest thing about here is it is a weighted average. It's a weighted average. What do I mean by weighted average? You are multiplying K1 with 1 with K4. So sum the coefficients. 1 plus 2 plus 2 plus 1. What is it? 1 plus 2 plus 2 plus 1. 6. That's what you see in the denominator here, 6. So therefore, it's a weighted average of the coefficients. Okay. So 1 by 6 times K1 plus 2 K2 plus 2 K3 plus 1 times K4. Now, what are these K1, K2, K3, K4? So Runge and Kutta devised that K1 is equal to, observe that if you put K2, K3, K4 equal to 0 and there is no 6 here, okay, then it returns to the Euler method. If you only take K1, no 6 is there in the denominator, K3, K4 all are 0, then is it an Euler method? Are you able to see it's an Euler method or not? Hmm? It's an Euler method? Yes. What is Euler method? Euler method is ui plus 1 equal to ui plus h times f at ti ui. Right. So this h of fi ti ui is k1. Nothing but K1. So if you don't have this 6 and all of these are 0, then this method just boils down to the Euler method. How it is Euler method? Yeah. How it is Euler method? Yes, that you have to see the derivation. But what I gave you a catch is the coefficients you have 1 into K1 plus 2 into K2. Okay, actually it is like W1 K1 plus W2 K2 plus W3 K3 plus W4 K4 such that W1 plus W2 plus W3 plus W4 will be 6 in your case. But if you want to, no, that is a mismatch. That is a mismatch. It won't be there. The last K you will always have will not have that by 2. But all other before that will have, the first one will not have, last one won't have. All other in between will have. Got the idea? So understood, no? So this is like for Euler. All other you are adding is by Runge Kutta. Okay, what you do? K2 equal to H times F evaluated at Ti plus H by 2, comma Ui plus K1 by 2. So it is using the information of K1 in K2. Okay. When you are doing K3, H by 2 Ui plus K2 by 2, it is using the information from K2. When you are doing K4, it is informing the value of K3. But mind you, there is no by 2. Ti plus H, comma Ui plus K3. There is no by 2 there. Okay. You understood this method now. Is there anything before we go to a problem? We'll solve a problem, then you will understand more clearly. Okay. Shall we do a problem? The same question we have, that solve the initial value problem, solve the initial value problem, du by dt or u prime is equal to minus 2t u square, given that u of 0 equal to 1, okay, with h equal to 0.2. We took h equal to 0.2 in Euler method also. We will take h equal to 0.2 in the Runge-Kutta fourth order method also, RK4 method also, and we'll compare which one is accurate. Okay. So use fourth order, classical Runge-Kutta method. Okay. Okay. Can we start? Can we start? So what is your first task? What is your first task? For at I equal to 0, suppose you already have t naught equal to 0 and u naught equal to 1. So can you tell me what is K1, K2, K3, K4? Because then only you can find what is U1, no? So K1 is equal to, apply the function h times f of t naught u naught. So that is equal to what? Then find u 0.2, that is u1. Okay, that means u at 0 plus 1 by 6 into K1 plus 2 K2 plus 2k3 plus k4. U of 0 we already know. U of 0 equal to 1. Can you tell me? K1 is equal to h into f into t naught u naught. What you got K1? 0. K2? K2 is h times f t naught plus h by 2, comma, u naught plus K1 by 2. What you got this one? 0.04. Minus 0.04. Then K3 equal to t naught plus h by 2, u naught plus K2 by 2. So that you got minus 0.0384. K4 h into f of t naught plus h u naught plus k3, right? So what is this value? Minus 0.07397, right? So what should be u at 0.2 is equal to u at 0. U at 0 is 1 plus 1 by 6 times what you got? 0 minus 0.08, then minus 0.0768, you will get minus 0.0739. So that you will get around 0.9615. So you got u at 0.2, 0.9615. Okay. Now, can you compute next value? Our next is u 0.4 equal to how much? Can we compute? So u at 0.4 is equal to u at 0.2 plus 1 by 6 times k1 plus 2k2 plus 2k3 plus k4, where k1 is equal to now h into f of what? F of t1 u1. T1 u1. K2 equal to h of f t1 plus h by 2, comma u1 plus k1 by 2. K3 equal to h times f t1 plus h by 2 u1 plus k2 by 2. K4 equal to h into f t1 plus h u1 plus k3. So each of these values is how much? Then we can find u at 0.4. We got this. Now we want to find u at 0.4. Can you do that? Tell me. So what do we understand from this? That's the main question. So you got u at 0.2 is 0.9615. Okay. So what I will tell is, all of you should tell me this. Okay. We will make a table. So u exact, u Euler, and u RK4. Okay. So this is t. So at t equal to 0.2, u exact is, I solved it. Can you tell me? 0.96. And u Euler, u at 0.2, and u RK4, 0.9615. Then next value, u at t equal to 0.4, u exact is 0.862. Then u Euler is 0.795. U RK4 is 0.8620.0525. Can you see what is happening here? This is the data we have for RK4. Can you see what is happening? So you saw that if you solve the ODE exactly, okay, you are getting the exact value at, sorry, at exact, you will get at t equal to 0.2, you will get exact value at 0.96. And the same at RK4, you are getting 0.9615. Whereas Euler, you are getting 0.92. So RK4 is highly accurate because the difference between 0.96 and 9615 is 0.0001. 0.001. Whereas in RK4, it is 0.04 error. So RK4 has 10 times more error than RK4. Euler has 10 times more error than RK4. At 0.4 also, it is 0.862 is exact. Whereas RK4 is giving you 0.862, almost exact till 0.0001 decimal place. Whereas Euler method is giving you 0.75, where it is only 0.01 accuracy. Can you see? So which one is better? Yes, so RK4 is much more accurate than Euler method. Okay. So if you are asked that given a differential equation, compute the exact, compute the Euler, compute the RK4 method and compare and deduce your thoughts, you can do as per we did now. Okay. Good. So this is all about the differential equation solving by numerical methods using two methods, that is Euler and RK4. However, I did not tell you how this how this method actually came to existence. We never discussed that. Okay. However, if you want to know how this method came into existence, you can tell me and we can derive it. Okay. However, I thought that what is more important is to know this method and to do something in practice. Okay. And to solve a problem rather than knowing the inside and deriving it. However, if you're interested, we can derive in a separate case how this method came into existence. Okay. Good. So we'll look into some Python codes for now. Okay. How um, hmm? Yes. So this is Euler method. Okay. So you can see Euler method I am trying to solve, and the function I am trying to solve is just e to the power minus t. The function is du by dt equal to e to the power minus t. That's it. Okay. Got it? That's the function we are trying to solve. And I will use Euler method for that. Okay. So you can see h equal to 0.1 is my step size. And I am doing a range from 0 to 1 plus h. Okay. In terms of the step size h. So I am creating equi-space grid on the t direction. The same thing we did in our x direction. Okay. Yeah. Fine. Okay. Then this is the initial condition, s not equal to -1. So at t equal to 0, u value is -1. So therefore it is an initial value problem and we can apply our Euler method here. Understood? Okay. So you see what I am doing, I am applying the Euler method here. S at I plus 1 is equal to Si, the past, plus h times, sorry, plus h times f at ti comma si, the past values, the Euler method, and I am looping it in for loop for all values of t, all equispaced value of t, and I am storing that result in the array S. Okay, and then I am printing it. Okay, I am printing the solution, exact solution. The exact solution is labeled as exact, and the exact solution is minus e to the power minus t. And this S is the approximate solution by the Euler method. Okay. And you see, I am plotting it and you can see the solution. The blue one is the exact solution. X-axis is the T, 0, 0.2, 0.4 like that. And you can see our Euler values are sampled at the step size of 0.1. So therefore, red values you see at 0, 0.1, 0.2, 0.3, 0.4, 0.56 up to 1. Okay, because we took our step size as 0.1, right? But the exact solution doesn't matter this. Exact solution is just a function, minus e to the power minus t, that is shown in blue. And you can see that as the time increases, the error is increasing. Okay, cannot see the difference much, but from this one, you can see that initial value, it is very close, then started getting separated out. This tells you a very important fact about Euler method, that as you integrate the Euler method, as you keep on iterating the Euler method and generate your solution, the error effect, yes, the error effect gets compounded. Okay, the error is transversed into each iteration again and again. So therefore, the error gets multiplied again and again, and its compounding effect. So as you increase the number of iteration, the error keeps on increasing. Okay, good. But apart from any other method, you can directly use the ODE int. Okay, import ODE int package directly from scipy.integrate. Okay, class, and you can directly use ODE int. Okay, without using any of these methods. Okay, so how it works? So you tell f is a lambda function, f is lambda x defined as 4 sine 2t. This is a very complicated equation which I gave you. Okay, which the question I gave you, can you try to solve it using ODE int? That's an assignment, computational assignment for your class. The complicated function I gave you, can you use ODE int to solve it? Okay, so I'm defining the function right here, and as usual, I am creating the equispaced grid in t direction. T is equal to 0 to 20 in 401 steps. Okay, understood? So this is our initial condition. X naught is 0.1. Okay, so it's an initial value problem, right? And I am doing x equal to ODE int, and I am passing some comments, some inputs. I am passing what is the function, the lambda function. I am saying what is the initial condition, that is x naught 1, that is 0.1. And I am passing the array t, that is np.linspace. So it's a grid. It's a equispaced grid. Okay, I am passing the function. I am passing the values of the x, that is t, independent variable t, 0 to 1 in 401 steps, and I am stating the initial point also. Now ODE int will do all the things for you. Okay, so you can see I am plotting x, t comma x, plt.plot t comma x in orange color. Okay, let's see how it looks. Okay, so this is your exact solution for that. Okay, this is your numerical solution. Okay, however, it is not clear why you got this solution, but one thing is clear, is something is periodic, but it is amplitude is decreasing as time is increasing. Can you see the amplitude is decreasing as time is increasing? Is it clear? You cannot obviously deduce. You have to take an easy problem and check whether it is correct or not. But I have taken a very complicated function involving sine, exponential, and x square and all those things, and I have showed you that you can get a solution out of it. Okay, so ODE int is a package you can use for solving differential equations, complicated differential equations in Python. Okay, irrespective of using Euler or RK4. They might be using lot of complicated methods inside ODE int package. Okay, fine. Okay. A similar thing is solve IVP. Similar to ODE int, another idea in Python is solve IVP. Okay, so solve IVP we will see. Again, you import solve IVP from scipy.integrate. You were doing the same thing in the before program. That's from scipy.integrate import ODE int. Same here, from scipy.integrate you are importing solve IVP. So that means if you have an initial value problem, you can use solve IVP without using lot of loops and RK4, Euler and anything like that. Just it wants to know what is the step size, what is the right hand side of the function you want to integrate, and what is the array of the independent variable. That's it. Okay, then it will solve the ODE for you. Okay, it will generate the numerical solutions. So how we will do that? You can see again, f is a lambda function cos t. If it is cos t, du by dt is cos t, what is u? Sin t, isn't it? Sin t. If you differentiate sin t, you will get cos. So the answer should look like sin, isn't it? The answer should look like sin. Let's see whether it is the case. Okay. So what I am doing, t val is np.arange 0 to pi, and I am dividing them into equispace 0.1 step size. Okay. Then what I am doing, solution solve variable equal to, I am storing the solution in solve variable. Solve IVP, this is what we will use now. F, capital F is your lambda function, that is cos t you are passing. Okay. And this is your evaluation grid 0 to pi. Okay, 0 to pi. And this array 0 you are passing. T eval equal to T eval. T eval is nothing but your array, the independent array, independent values you are storing. Okay. And these are all plotting issues. I'm not going there. So this is the solution you are plotting here. Okay. So you see pi by 2 is how much? Pi by 2, pi is around 3.14 something. By 2 is around 1. What? 1.5 something, right? So around 1.5, you are getting one value almost. So that means it is a sine function. At 0, it is 0. Okay. At 3.14, again it is 0. Sine pi is 0. Sine 0 is 0. Sine pi is 0. Sine pi by 2 is 1. So all this quality you can see in this plot. Is it clear? Is it clear? What is the value of the curve at 0? 0. 3.14 at this point, 0. At pi by 2 around, yes, so it will be around 1. So sine pi by 2 is also 1. So this is the solution of sine. And we predicted that because du by dt is cos. So it should be u of t should be sine, right? And you are plotting it. What we are doing here is s of t minus sine t. We are plotting the error here. How much difference from sine it is getting. And you can see this is the error. And you see the error is very small. 0.000 10 to a -3, -4 range error is there. So solve IBP is giving you a highly accurate result. Okay, so you can see that. So the take home message is solve IBP and ODE are your rescuers. If you have a very complicated ODE in front of you, you can use it. Okay, I hope many of you who are doing capstone project involving different ODEs already must be using ODE, right? Yes, ODE. You must have seen ODE, right? You must have also seen. Anyway, there is another model, whether I'm checking whether we should do that. Okay, we'll do that. Okay, this is RK4 method we are looking. This is an ecological problem actually. Most people from ecology background, ecological informatics, they usually study the population dynamics. Okay, population dynamics means like why in a forest lion is always strongest. So why we only see why still now we see deers? If lion is so powerful and eating deers, why we see deers? Lion would eat all deers. So why deer still exist? Can anyone answer me? Why deer still exist? If lion can eat the deer, why deer still exist? Yes, it's a population dynamics. The population dynamics is such that lion, if he eats lot of deer, by eating lot of deer also, lion will die. So lion knows that, and lion will eat only limited amount of deer, and after that he will say stop, don't eat more. Okay, to save himself. So deer in that case will grow. Okay, and the lion who has eaten lot of deer will die, and new lion take place. So like that, there is a balance between the population of deer and population of lions. Okay, however, they are not constant. They're oscillating. Every time they're oscillating. They're oscillating in such a way that there is a balance. So this is the population dynamics one wants to study. And Worst model is one such model to predict the dynamics of those lions and deers in ecology surroundings, how they maintain their population. Why there are no deers? Okay, why always there is a deer count? So this model explains that. Okay, so I will not tell much into deep, but if you are interested, we can discuss it more. Okay, but the idea is something same. Like you have this X population, deer population. X is a deer population, and you normalize it. I mean, the highest population the deer can reach is 1. Normalized population. 1 can be 1 lakh, 1 can be 1 million also. But we are normalizing, dividing by 1 lakh. 1 lakh by 1 lakh is 1. Okay. And 50,000 by 1 lakh will be a value less than 1. Okay. We are normalizing it. Okay. So therefore you see 1 minus X by P. Okay. I mean, 1 is a total population minus how many are there. So total population. How many are being eaten by lion? 1 minus X by P. Okay. So this is the model, and we are using the Runge Kutta method here. You can already see. Okay. So you can see the same method. K1 is equal to f of t I minus 1 the past. K2 equal to Ti minus 1 plus H by 2, Xi minus 1 plus H into K1 by 2. Okay. Same thing. And K4 also, you already know. And where? Yes. Okay. So yeah. Are not we doing that? Are we not doing it? Check that it's the same. It's the same. No. Check that this K1, I was multiplying H outside. I was multiplying H outside. That same I am multiplying inside. Isn't it? You got the same, no? There are different versions, but I did not use this version in your case because it's a bit more confusing. I thought that multiplying H outside in all the cases is a bit easier than multiplying inside. But check that it is the same. Check that it is the same. Okay. So you can see that almost it matches. The black one is the Runge Kutta method one, and the cyan one is the exact one. And you can see from the start till the end of the simulation, RK4 method exactly matches the exact solution you are getting. Okay. This is just a simple problem we have taken and illustrated it. However, you can go to much more complicated method and solve it. Okay. There are Lotka-Volterra method also, where now I told you ODE with one variable, no? Dx by dt equal to a into x into 1 minus x by p. But there can be two variables. There can be two variables, no? Two variables, by two variables I mean dx by dt equal to ax into 1 minus y square x and dy by dt equal to say bx by into 1 minus x square y. Isn't it? There can be complicated equations like this, which many capstone projects are doing this. Many capstone project students are doing these methods, right? So what has happened? X depends on x and y. Y also depends on x and y. So it's a coupled equation. It's a coupled equation. So you can use RK4 to solve this equation also. RK4 is so powerful. However, I have not taught you that how to do, but the same thing. For x variable, you will have K1, K2, K3, K4. For y variable, also you will have L1, L2, L3, L4. Same formula, same formula. So that's what you are seeing in the Python code. Kx1, Kx1, Kx2, Kx3, Kx4, Ky1, Ky2, Ky3, Ky4. Okay. Same formula, but looks very complicated. Okay. But it will solve you and give you the result. Okay. It will solve you and give you the result. See, it shows that predator and prey. Predator means lion, prey means deer. They're oscillating. Their population is oscillating. Population in thousands. They're oscillating. They're not constant. They're oscillating, but oscillating in such a way that they are maintaining a balance. Okay. You see, they are oscillating in a constant way. Okay. But see that predator population is always more than the predator. Sorry, prey population is always more than the predator. But if you change the parameter, for example, it is a cold day, it is a winter, it is winter, then lion will hunt deer every time. Okay. Then what will happen? Population of deer will come down and population of tiger will increase. Okay. If it is a hot day, then the tiger won't go out because it's very hot. Okay. Then it won't eat that much deers. Okay. Then deer population will be high. So depending on the parameter and season, the population of one predator and prey can change. This is monitored by these parameters actually. A, B, C, R, and all these the model parameters you can change based on the season. Okay. Yeah. So there are these boundary value problems, but we are not discussing boundary value problems because it's a bit more complicated and involved. If you want, we can discuss. Okay. So fine. This is what I wanted to cover in ODE. Okay. So what is the take home message? ODE, we saw that you have initial value problems. Okay. Initial value problems means the initial value is given and you are computing y at that initial value. Then only your differential equation will have a unique solution. Otherwise, the ODE has infinitely many solutions. And there is no point in talking about infinitely many solutions. It is not useful for us. Therefore, we fix a initial condition and we get a unique solution. Okay, so now if you have an initial value problem, we have a unique solution. Based on that, we devise two methods. That is Euler method and RK4 method. We used Euler method, we derived Euler method and saw that Euler method is not that efficient, but it's a good method. Okay, very simple method. We devised RK4 method also, Runge Kutta fourth order method, and we saw that RK4 method is highly accurate. It is taking K1, K2, K3, K4 and yi plus 1 is equal to yi plus 1 by 6, the weighted average, K1 plus 2K2, 2 plus 2K3 plus K4, where you already have what is K1, K2, K3, K4 listed in your case. Okay. And we found that RK4 method is highly accurate. 10 to the minus 3, 10 to the minus 4 accurate. Error in the range of 10 to the minus 3, minus 4. We also saw the Python implementation of Euler and RK4 method. Okay. We also saw that if your values are like coupled equation, RK4 method can solve that also. Okay. We also saw that there are two packages from scipy.integrate, that is ODE int and solve IVP, where no knowledge is required. You just need a lambda function f and the independent array you have to pass, and the initial value should be passed as argument to the ODE int and solve IVP. It will give you the output, the data. Okay, and you can plot it. Okay, so this is all about ODs. So any doubts so far? Any doubts?